Topic 3 for advanced HVAC science is going to be thermal expansion. And just a reminder as we start to pile on more formulas, what we've covered so far, we were talking about finding heat flow or transfer, which is represented by the variable Q, from a material's thermal conductivity, which is represented by the variable K. So when we move into thermal expansion, we're not going to be finding heat flow or transfer. We're going to find a change in size due to heating or cooling of substances, both solid and liquid. The rule is that if you heat something, it's going to expand in all directions. If you cool something, it's going to contract. Now we have one exception, which we'll talk about at the end, but as you heat something, as the temperature rises, the molecules, remember, that are in that substance are vibrating faster, so they are taking up more space. They need to expand because of their increased vibration. And the opposite happens as you cool a substance. Now, these are small changes in size, very small for solids, a little bigger for liquids, but they do matter. You think about expansion joints in a bridge, like how much liquid can your container actually hold if you're going to heat it, that kind of thing. So what we're going to cover is linear expansion, area expansion, and volume expansions, all for solids. But we're also going to cover volume expansion of liquids. And here's me harping on this again. When heated, solids expand in all directions. When cooled, solids contract in all directions. But sometimes we have a solid that is very, very long and thin, like a railway tie or a pipe or a rod. And we can treat this like a line. So we think of expansion and contraction as going, just in one dimension. So linear expansion deals with long, thin solids, and it's one-dimensional. What does it depend on? What the object is made of. Copper has a different expansion rate than glass. Your length, your original length. The more length you start with, the more expansion or contraction you're going to get. And of course, your temperature change. If you have a bigger difference between your starting and finishing temperature, you're going to have a bigger expansion or contraction. So let's learn the formula. It looks crazy. So the first thing I want to talk about is that triangle. You see it in two places, right here and right here. And that is not a variable, like that's not time or, length or volume. That is a Greek letter delta, and that means change. So when it's in front of a T, that's a change in temperature. So the new temperature, which I call T2, minus the original or the old temperature. And it doesn't matter which one's hotter or colder, right? It'll work out with a negative if you're cooling, and it'll work out with a positive number if you're heating. And when we see it in front of this little L here, that same thing. It means a change in length. So treat this as one variable, not two. And when you see all these symbols smashed together on the right side of the equation, that means they're all multiplied with each other. So let's start. A little bit of a highlighter. That is a change in length. Okay, and the neat thing about this is it doesn't really matter what the units are, as long as they correspond to the units over here for the original length. So if you put in to this formula inches, you're going to get out inches. If you put in millimeters, you're going to get millimeters out. If you put in kilometers, you'll get kilometers out. So just don't care what the unit of length is, just make sure it'll be the same in and out. We have this crazy symbol. It looks like, I call it the fish. It's alpha. It's another Greek letter. And in this formula, it is called the coefficient of linear expansion. And this is a constant. This is like K was, the thermal conductivity. I have to give it to you. So there'll be a coefficient of linear expansion for a material, say brass. And there'll be one number for if you're working in metric, and one number if you're working in imperial or US customary. Okay, so you have a table on your formula sheet that has the values you might need. We already did our L is the original length in the same units as the change in L. So not the new length, not the length you're going to make after heating or cooling, it's the original length. And delta T right here is a change in temperature. So it's either going to be Celsius, I guess, or Kelvin, or on the other side, it'll be Fahrenheit or Rankine, and it'll be in units that are matching what you'll see on the table for the coefficient of linear expansion, alpha. And once again, just recognizing that if you start at 20 degrees Celsius, that is your temperature 1. And if you heat it to 50 degrees Celsius, your change in temperature will be T2 minus T1 equals 50 minus 20 equals 30 degrees. So now it's time to math it up. Here we go. So first thing, I'm going to write down my formula. The change in length is equal to the coefficient of linear expansion multiplied by the original length multiplied by the change in temperature. So I'm going to look to the question, 5 meters, there's my original length. Write it down. Okay, and we're heating from negative 30 to positive 30 in Celsius. So my original temperature is negative 30. My new temperature is 30. So my change in temperature is T2 minus T1. So 30 minus, and watch this, negative 30. So punch that into your calculator or know how negatives work, and you'll see to go from negative 30 to positive 30, you actually cover 60 degrees Celsius. The last thing I need is to find my coefficient of linear expansion. So I'm in copper and I'm in metric. So copper, metric, this is the number I'm going to use. In class, we will go over scientific notation to make sure you have it down, but I'm going to blow through it for these YouTube videos. All right, and just while we're here, look at these values, right? Like, which ones are the high ones, which ones are the low ones? So if you have 10 to the minus 5, aluminum has a higher coefficient than, say, Pyrex at 10 to the minus 6. Even though the number 3 is bigger than the number 2.3, it's all about what the exponent is. Okay, enough. Here we go. So I'm going to take that formula, my change in length. I decided I was going to use 1.7 times 10 to the negative 5 for my coefficient of linear expansion. My original length was 5 meters, and my change in temperature is 60. When I multiply those all together, I get 0.0051, and the unit is the same as what we put in, which was meters. So that's my change in length. When you heat copper by 60 degrees, you're going to get a change in length of that pipe of 5 millimeters. It doesn't seem like a lot, but it matters, right? It matters where this pipe is. So what's my new length of the pipe? I take my original length, and because this is an expansion and a positive number, I know that I'm adding it. The pipe is getting longer, and my new length will be 5.0051 meters. So to try and make this seem remotely relative to you guys, let's talk about when our thermostats used to have bimetallic strips in them. So what happens there? You take two different substances. Here they've got copper and iron. And what I know about copper, let's just say we're going in metric. It has a coefficient of linear expansion of 1.7 times 10 to the negative 5 per degree Celsius. Whereas iron has a coefficient of 1.3 times 10 to the negative 5 per degree Celsius. So what does that mean? When you heat them, looking right here, copper is going to expand more than the iron expands. So whatever. But if you glue them together or bond them or however you're going to do it, I'm sure there's some magical welding you can do. Suddenly, if the copper is tied to the iron, how can it get longer than the iron? Only by bending, right? So we have a greater length when you're on the outside of the arc versus the inside of the arc. So that's what happens when you bond them together and you heat them. Now, if we were to take this even further and clamp one end, then heat it, due to the copper wanting to get longer, it's going to bend away from something. And what is that something? That's some kind of contact, right? So as you heat a room, the contact opens because the copper expands more. And then as the room cools down, as the temperature drops, it slowly goes back to a straight line. The contact is made again, and that signals the furnace to provide more heat. Now, they're not just a strip in old thermostats, they're a full-on coil, but that's the general idea. Whenever we have a solid, we are always using the coefficient of linear expansion. But the nature of the solid, the shape of the solid, changes the formula that we use. So we already talked about our long, thin pipes or rods, and those use a change in length is equal to fish times the original length times the change in temperature. Okay, but if you are talking about area expansion, what does that object look like? It would be a flat plate. Okay, so like something like a sheet of paper, you're going to use area expansion for. Pro tip, if they're asking you to do it, you're only going to get 2 dimensions. They're going to talk about, you'll see the word flat. You'll see the question area, or the word area in the question. So this is area expansion. And if they give you 3 dimensions or start talking about volumes, or you see cubic units, we're talking volume expansion. Okay. How does it change the formula? Everything looks the same, except you have a multiplier in front. So think of it this way. Area is 2 dimensions. Bring in the 2. Volume is 3 dimensions. Bring in the 3. And remember, we're going to get another volume expansion formula in a second, but this one is for solids. Anything that uses alpha, that fish, is expansion of a solid. So let's look at an example. I haven't told you which one it's going to be. Well, I kind of have down here in the formula, but I see the word area. And I see a unit that is squared. So I don't have to do a calculation to find an area, but you totally might have to. You might have to find the area of a rectangle, or which is length times width, or you might have to find the area of a circle, which is pi r squared. Those are fair game because we know those kind of things. But for this one, we've outlined it here. We're going to use the change in area formula. Change in area is equal to 2 times the coefficient of linear expansion. This is the new thing, times the original area, times the change in temperature. Okay, so let's start with the original area because it's the first thing I see written down. 3 meters squared. Our first temperature, our original temperature, is 10 degrees Celsius. We're back in metric. Our next temperature, our new temperature, is negative 10 degrees Celsius. So remembering that the change in temperature is equal to T2 minus T1, if you do that math, you get negative 10 subtract 10 equals negative 20. Oops, put the negative in, negative 20 degrees Celsius. So this is method 1, where you can force yourself to recognize that this is a contraction and a cooling, because when you do the math, you get negative. So that means cooling or contraction. Or if you prefer, you can always do big number minus smallest number, but then you have to remember whether the object is expanding or contracting and correct at the end. We'll see when I get there. Okay, what else do I need to know? I need to know the coefficient of linear expansion for steel. I'll put it right up here. I need the metric one. Don't pick the imperial one. 1.3 times 10 to the negative 5. We're going to build the formula. The change in area is equal to 2, and that is just this 2. It's not anything else, times the coefficient of linear expansion times the original area times the change in temperature. So this tells me that I have a change in area of negative 0.00156 meters squared. Am I done? Most people walk away, be like, high five, I got it. Read the question. They don't want the change. They want the new area. Okay, so we're going to take our original area. And what are we going to do? Well, there's a negative in front of this. That means contraction. This thing is getting smaller because we're cooling it. So this is the math. New area equals 2.99844, lots of digits, meters squared. Let's do another example just to see how we can switch it up, and that would mean I'm asking you to solve for something else. So here we go. Area, see the word right there? So we know it's the area formula. The change in area is equal to 2 times the coefficient multiplied by the original area multiplied by the change in temperature. I see it's contraction, so you have a choice here. You can make things negative, and I'll do that, but it'll work out just fine if you leave both the two things that could be negative positive. That's confusing. All right, what are we solving for here? The initial area. What do we know? That it contracted by 0.025 square feet. So we know that is the change in area. And because it's a contraction, I am going to throw in the negative. And we see that the temperature change is no math required. It was given to us, and it was a contraction, so I'm going to throw in the negative. So you can see if I have two negatives here and here, I could have just not had them. The math will work out the same. So it's whatever you're most comfortable with. Last thing, we need the coefficient of linear expansion of concrete. That is in imperial. So I go to my formula sheet and I see that it is 6.0 times 10 to the negative 6 per degree Fahrenheit. Let's put in what I have. I have a change in area. 2 is just a number. My coefficient of linear expansion. I'm looking for this. And I have negative 90. I'm going to clean it up on the right side by doing the multiplication that I can. And I'm going to have left side stays the same. And when I multiply those three numbers together, 00108, and I still don't know A. If I want to isolate A, you always divide by everything that is in front of the variable, the letter. So I'm going to divide by that negative. Take the negative with you. If I do it on the right side, algebra says I have to do it on the left side as well. These two will cancel. And when I do this math, I end up with 23.15-ish square feet. And that was the original area. If you're not sure, just go back and do the formula and see when you use this 23.15, if you put it in for A, are you going to get 0.025 when you solve for the change in area? The last shape that we can expand or contract is something that has 3 dimensions, so that requires volume expansion. So let's look at this one. So we have concrete as our material. We're working in metric, and we have 3 dimensions, so I'm just going to assume that we're talking about a block here, a rectangular prism, and not to scale at all. Let's give this 30 meters. Let's give this, oh good lord, 6 meters, and give this 12 meters. So our volume, our original volume, will be 6 times 12 times 30, which is going to be 2,160 meters cubed, 3 dimensions. All right, what else do we see? We see that our original temperature was a hot day, 38 degrees Celsius, but it sometimes turns to winter and it goes down to minus 15 degrees Celsius. So if we want to know the change in temperature, T2 minus T1, this will tell us that we are contracting as well, negative 53 degrees Celsius. What else can I figure out? I know that the coefficient of linear expansion for concrete in metric from my formula sheet is 1.1 times 10 to the negative 5 per degrees Celsius. All right, let's set up the formula. Change in volume. You need to pick the one that talks about 3 dimensions, has a 3 in the front, and uses the coefficient of linear expansion because we're talking about a solid. Original volume change in temperature. So we have 3 times 1.1 times 10 to the power of -5, and we have 2160 as our original volume, and we change the temperature by 53 degrees. Finishing the math, the change in volume would be -3.778 meters cubed, which means that when you drop that temperature to -15 degrees Celsius, you can expect this block to contract by that amount, and you better have allowances built in for that. Our final topic or formula in thermal expansion will be volume expansions of liquids, and we're only going to talk volume or capacity for liquids because we don't deal with them in 1 or 2 dimensions. We consider them always to be in 3 dimensions. So the formula looks familiar. We've got a change in V. We've got an original volume, oops, let's make that a big T, times a change in temperature. But we've got a new variable. Okay, so recall that for changing the volume of solids, we had the change in volume is equal to 3 times alpha times original volume times change in temperature. Well, this B is called beta, comes right after alpha in the Greek alphabet, and we use that only for liquids. It's called the coefficient of volume expansion, but it's only for liquids. Another dead giveaway is when you go to your formula sheet and you try perhaps to use this formula incorrectly for a solid. When you look at the list of materials, these are all liquids, so good luck. Try to use that for concrete or something like that. Okay, so keep it in mind and don't stick a 3 in this formula. It does not have the 3 like the solid formula does. Okay. And you'll notice these numbers on the volume expansion, they're much bigger. Like they're not 10 to the -5 or 10 to the -6 or 10 to the -3 or 10 to the -4, which is many times bigger because volume has a greater ability to expand. Liquids have a greater ability to expand and contract than solids do. So one example for this, volume in, volume out, same rules as the other formula. So we have an original volume of 250 liters. We need to find the coefficient of volume expansion for water in metric. And if you go to your formula sheet, you'll see that it is 2.1 times 10 to the -4 per degrees Celsius. I don't usually write that down because it looks like part of the thing, so I'm just going to box it off. And how about our change in temperature? We started at 15. We ended at 40. Our change in temperature is T2 minus T1. 40 minus 15 equals 25 degrees Celsius. Recall our formula is a change in volume of a liquid is equal to the coefficient of volume expansion multiplied by the original volume multiplied by the change in temperature. Putting our numbers in, 2.1 times 10 to the -4 multiplied by 250, the original volume, multiplied by the temperature change. So not a big temperature change. Let's see what happens. As we get that answer, 1.3125 liters, we see it's quite a bit more significant than the amount of volume change you were getting from the solids. 1 liter is nothing to sneeze at. So there's an example of liquids. And we have to be very careful. We'll never let these, we'll never put water in a range where it might freeze or boil. So we as professors will be cautious about the temperature ranges we give you. I mentioned in the start there was one exception to the rule that things contract when cool and expand when heated, and that is water between 0 and 4 degrees Celsius. So once you hit 4 degrees Celsius, water hits its minimum volume. It's at its most dense, which is very, very unusual because usually that would happen right before you changed phase. Oh, that's coming. And froze. But water gets down to dense at 4 and then actually becomes less dense or expands. When it freezes, it jumps up. Oh, that'd be way up here. And expands by 9%. So this is how we burst our pipes. This is what allows ice to float on water and fish to live under ice in the winter. So it's very, very important, and it's very, very irritating if you're designing anything that has to contain water that might freeze. That's all I have to talk about for thermal expansion. We will do a lot more examples in class, but I just wanted to make sure I got one up for you.